My name is Sean McCafferty from Tucson, Arizona. I am president and CEO of INTOR Technologies, which has proprietary patents on the tonometer prism I'm about to describe. We are discussing here the mathematical optimization process in producing a corneal thickness correcting Goldmann applanation prism surface. Goldmann applanation tonometry is identified as the gold standard by which intraocular pressure is measured. This has essentially been unchanged for 60 years. The assumptions made by the Imber-Fick principle and Goldmann have left considerable error in our IOP measurements. Most researchers agree that those errors include corneal stiffness or rigidity, which is an intrinsic property of the composite corneal material, corneal thickness, and curvature, which are geometric properties of the cornea, and the corneal tear film, which is an extrinsic property affecting the pressure measurement via surface tension fluid mechanics. The problem lies, as far as the error is concerned, in the large individual variability amongst patients. Corneal thickness, shown here, can vary the intraocular pressure by plus or minus 7 millimeters of mercury, the corneal curvature by plus or minus 2 millimeters of mercury, and the corneal rigidity by plus or minus 8 millimeters of mercury. Lastly, the corneal tear film by plus or minus 5 millimeters of mercury. Fortunately, the last two tend to negate each other as they usually err in the opposite direction, but not to the same degree. Regardless, the cumulative error can be substantial, and some researchers have concluded that while subsequent readings from individuals are useful to guide treatment, readings between individuals are too error-prone to be of significant clinical use. Finite element analysis modeling using a nonlinear anisotropic composite lamellar corneal model of collagen fibers set in a ground substance substrate is used to verify the biomechanical properties of the cornea and predict its behavior under mechanical stress. This model has been perfected by us over the last 20 years of research. Shown here is the standard flat Goldmann tonometer prism surface applanating the cornea in cross-section. Note the conformation of the rigid flat surface and extensibility of the remaining unapplanated cornea. Our design optimization process utilized and verified finite element analysis modeling to flatten the isobaric curves of the simulated intraocular pressure with respect to the parameters which cause error in our Goldmann applanation tonometry. We are attempting to create a Goldmann applanation tonometer which is independent of corneal thickness, corneal rigidity, corneal curvature, and tear film. The best solution shown here is a polynomial approximated central concavity with a peripheral convexity that minimizes the effect of the error-causing parameters. The key to the optimization process is minimization of the intracorneal stress during applanating deformation. Shown here is the average intracorneal stress at a given applanated radius from the corneal apex. Note the stress maximum occurs at the transition of the unapplanated cornea. Minimization of this transitional stress also minimizes the corneal contribution to the measured intraocular pressure, which is of course the source of error. The comparison between the standard GAT and the two optimized designs are indicated here. Finite element analysis modeling optimizes the applanating surface to minimize the tonometer force contribution due to the average modulus of elasticity as well, or corneal rigidity. Flattening the rigidity dependence curve on the modulus of elasticity is shown here by comparing the increased error with the standard flat GAT with the more independent optimized surface, which leads to approximately plus or minus 2 millimeter mercury error correction for known individual variation. A similar significant reduction in the IOP measurement dependence upon corneal curvature is found with the optimized Goldmann applanation tonometry surface. Again, we do not typically correct for errors in corneal curvature nor in corneal rigidity, only in corneal thickness. Shown here is a primary prototype of the optimized design with a modified biprism surface. Additional prototypes are forthcoming. As an initial test, we clinically compared our primary prototype in vivo to the standard flat prism surface. While these numbers are preliminary, and on a limited number of patients, we did see a trend toward what would be a significantly reduced error due to the variation in corneal thickness. The reduced error is also in line with predictions made by the mathematical model of approximately plus or minus 2 millimeters of mercury for 95% of the population. The advantage is that this is significantly improved optimized Goldmann applanation accuracy of plus or minus 2 millimeters of mercury for 97% of the population compared to the standard plus or minus 7 millimeters of mercury with the standard Goldmann applanation tonometry, correcting just for corneal thickness. Also, the advantages include that it further corrects for corneal curvature and rigidity, which are clinically ignored at this point. In addition, it also reduces the error due to the tear film meniscus, not included in this analysis. There are some potential effects in clinical practice. This method would be very inexpensive and easily adopted with minor modifications to existing technology. Increased intraocular pressure accuracy over the standard Goldmann applanation tonometry with central corneal thickness correction would make it the new gold standard. Significantly improved intraocular pressure accuracy with compound error correction for corneal rigidity, or simultaneously with corneal rigidity, curvature, and tear film is also an advantage of this design. It may negate the need for pachymetry correction in Goldmann applanation tonometry at this point. Future directions for the modified Goldmann applanation tonometry surface are human testing and verification. Additionally, we want to measure corneal curvature, corneal rigidity, and corneal thickness, as well as tear film, and compare it to the intraocular pressure via cannulated transducer. We will also compare the standard and error-correcting optimized surface Goldmann applanation tonometer, and then proceed with FDA approval through a Class II 510K approval process.